build parts. I really like that. I had a PhD student who is now in Finland, Sneha. She did some outstanding work on at least thermal post treatment. She was also another student of mine who is now working on surface post treatment, and my colleague Magnus. So I've taken some of their slides. So if you look at uh, the number of steps in AM, we spoke about this earlier, no? Modeling, STL files, slicing, etc., printing. So we have kind of covered up to here, and on the back side here, feedstock, etc. Now post processing. We will talk about why post processing is crucial for almost all applications, right? And these are almost mandatory now before we go on to a finished part that is ready for application, right? Uh, this is another way of showing the same, right? After processing, you need to do. I'm not, as I said yesterday, I will not deal with uh, grid blasting and removing the surface plate as post processing. That's part of processing only for me. Yeah, the real post processing really is uh, uh, surface, changing the surface attributes and doing thermal, right? And we'll talk about why we need to do that, right? There is, at the end of this loop, there is certification as well, as I mentioned briefly in the morning. And that's something we will cover on Friday. Deepa will come and talk about certification a little bit, right? So those are important things. Uh, why post process? Yeah, because a produced part, people can talk about near net shape, this, that, but it is never completely ready to use, right? You need to do several things, and we'll talk about why. Yeah, and this is what you do is both process dependent and application dependent, and depending on that, you may need to use several additional steps before you can put the part in actual service, right? Uh, if you look at literature, people will talk about all of these things. Removal of excess powder, removal of support structures. For me, it's not post-processing, yeah? It's the end steps in a process, right? And then these two is what we will focus on. Finishing to obtain the desired surface attributes or geometrical tolerances, one. And second is treatments to improve mechanical properties, yeah? These two are very crucial depending upon which material you are using to build and where it will be used, right? In many cases, just an as finished surface may be okay, right? No problem. As built, I meant. As built surface may be okay to use. Sometimes it may need mirror finish almost, right? So it depends upon where you use that, right? We spoke about this yesterday. Let me get it out of the way because these are not really close to my heart. You remove excess powder. You saw a video on that, and then this is more necessary in powder bed fusion. In DED, you don't need that. Yeah, you just need some normal machine cleanup. If some powder that you have delivered has not melted and deposited, you just get rid of that. Just a simple high pressure air blast will do. You don't need to do anything more than that, because in case of DED, the part is not covered in all sorts of stuff. Yeah, it's already there. So it's not encased in unused feedstock, right? Same with supports, right? This is a pain, but it's a necessity. It doesn't come off as easily as removing the powder. Most times you have to mechanically cut it off, right? So by applying force or by, we oftentimes use EDM wire cut to take it off, right? Yeah, over. The boring part is over. Now let's talk about surface post processing and thermal treatment. Yeah, these are important tracks. On the last day, I am going to give you a list for list of resources for additional reading. While I was compiling that last night, I thought I will put that here. This is a good resource for surface post processing. Very nice review paper in additive manufacturing. But let's talk a little bit about surface integrity of AM built parts. We didn't talk so much, but a typically built AM surface is rough. Yeah, the context may vary. How rough, that may change, but it's always rough. EBM is very rough, SLM is rough, DED locally is not rough, but on a macro scale it is undulating a little bit. Yeah, so all of these things are a fact of life in AM. And some people consider this as a disadvantage, but that's how it is. It happens because of the fact that all of these are layer by layer deposition processes. You just can't avoid not having a great surface. Right? It typically creates a ridge effect on both vertical and horizontal surfaces. I showed you one slide in VAM, for example, a single wall build, and you saw that the vertical wall had fairly lousy surface in that sense, right? So can't really help that. The ways to improve that in regardless of what method you use is to reduce the step size, right? You build it in smaller steps. We spoke about layer thickness between 50 to 90 microns or whatever. If you reduce the layer thickness, you get slightly better finish, but you are paying a price already. What's the price you are paying if you reduce layer thickness? What's the cost of reducing layer thickness? Who said that? Yeah, correct. You are directly increasing production time as you reduce layer thickness, right? So that's cost as well, right? So although you know that reducing layer thickness can yield better surface finish, it's two things. One, it is still not ready to be used, yeah, for many applications. You still need something. And second, it compromises productivity. So not a relief reducing layer thickness, yeah. But you may want to then address that surface roughness for a variety of reasons. Sometimes it could be simply because of assembly, it could be a mating part and you want a good finish. Sometimes it could be because of good looks, sometimes because of surface functionality, right? If it is rougher, maybe it is more prone to corrosion or things like that, or it gives you very bad wear in the mating part, could be anything, right? So you need to account for all of those things, right? What are the factors that affect surface roughness in a part? We very briefly just mentioned layer thickness, but there are many other things, right? The feedstock influences surface roughness. Do we all agree with that? Yeah, coarse powder, fine powder, it will affect surface roughness. How you design the part, and there is design freedom available, remember, but how you design the part, whether there are inclined features, whether during building, how are you orienting the part? Yeah, is it oriented in the build direction? Is it transverse, right? And which surface then has a greater roughness, right? So, so if you build a part, for example, I showed you the standard bread and butter build where you build the blocks. The roughness on the side is different from the roughness on the top, right? So for that reason, the part orientation also becomes important, right? Of course, process parameters, does it melt fully, does it melt too much, does it not melt fully, all of them also govern the surface roughness. We spoke about layer height already, but yeah, even the spacing between, if you're doing laser or E-beam, the hatch distance also influences that. So there are too many things that uh, influence surface attributes, but the fact is, whatever you do, the as-built surface is not ready to be used, right? You can do your best with all of these things, but it still requires some finishing. In addition to that, there are other things that we spoke about, spattering, for example, right? If you get splashing or spattering during building or stuff like that, that makes matters even worse, right? How do you surface treat? There are many ways to do that. Uh, if you look at how they are classified, uh, uh, generally people talk about techniques that involve material removal, and there are techniques that uh, kind of improve the surface attributes without removing material, correct? Uh, I, although it is in this chart, I am not talking about this yet, because people look at this as surface treatment as well, or surface post processing, but I want to deal with that separately, right? Because this is not merely to change surface attributes, but to get new function on the surface. So let's deal with that tomorrow when we talk about coatings, right? But material removal, then there are mechanical ways to remove material, there are chemical ways to remove material and smoothen the surface. There are also some laser based treatments, yeah. Uh, kind of very busy slide, right? Mechanical treatment, easiest if your final part demands it is machining, right? People do little bit of machining. That's pretty normal. It could be grinding or milling, but if you need to machine it eventually, no problem. Uh, you may want to not really machine, but just do polishing, right? To get rid of the surface asperities. So if you do that, that's there are various ways to polish, including ultrasonic and stuff like that. We have also published a paper on burnishing. How do you burnish, yeah, and reduce roughness? So that's possible as well, yeah. Uh, there are some groups that explore laser-based material removal, which could be either laser micro machining, or there are very fancy lasers that are available to do that. Yeah, but I recommend that you explore this only if it's absolutely necessary. It's just for me, this is a research track. Yeah, these are real tracks. Yeah, for application. I don't see this as a real application relevant track. It's just to do research. What happens if I do laser texturing? Yeah, nice fun to explore, but I don't think it's relevant for a real application. Yeah, there are other methods also that you should be aware of, where you can dramatically change the surface attributes, but you don't remove material. Yeah, what could those be? It could be just bead blasting, yeah, where you can use almost like shot peening, or grid blasting with softer beads, where you don't remove material, but yeah. Shot peening, as I said, is also widely used. A parallel to that is other laser based treatments, laser remelting, laser polishing, yeah. All of these can also be used to change the surface attributes, right? We will talk about some of those, right? And then we go on to thermal treatment. So talking to some of our industrial partners and making a list of things that they do, I will leave that here while we have tea. You can think about that a little bit. Yeah. Thank you. Just before the break, I was uh, talking about this slide. So from that very complicated uh, table on the previous slide, this one, I have tried to extract uh, some of the surface post-treatment tools, which according to my collaborating industrial partners, they use, right? So I don't have a particular favorite among these, but you must know that all of these things are available for you if you want to post-treat an AM build part to change the surface attributes, right? Machining, blasting, shot peening, and we have investigated some of these. We have also done some work on burnishing, as I was saying, yeah. And what is new? This is what was being done for a long, long time. But what is new is something that involves chemical and electrochemical polishing. This is a big thing now. There are new startups coming up in the US and in other parts. And as a part of one of the projects that we have in Sweden, there is a technique called Hertization. That's from a company in the US. And this institute called RISE in Sweden has been looking at Hertization. So I spoke to Swati and took some slides from her, right? Let's talk about what it is, right? I mean, we have already discussed this. The motivation for post-processing, whether it's surface roughness, taking care of internal defects, residual stress. I will come to these later, but what we are targeting right now is surface roughness, going from a part that looks like that to a part that looks like that, right? I mean, that's what we are trying to accomplish, right? So there are many material removal techniques, as I showed you earlier, and all of them are good, right? Here are some examples, again from the lab now, right? From the lab, what happens to the surface roughness if you do grinding, right? This is an as-built part, and depending upon how you grind, you can eventually get there, right? Grinding is simple, not so complicated, of course, depending upon what the part is made of, right? There are people now trying to also do by AM tungsten carbide. If you're doing tungsten carbide, then even grinding is very difficult because it's such a hard material, right? Milling, of course, you can get excellent surfaces if you choose to mill, no problem. There are some magnetic abrasive polishing techniques. So people are looking, the reason I am showing you this scientific looking slide is to emphasize that many research groups are now diving in, because they acknowledge that this is a big problem. Industry is going to need solutions to surface treat the build parts. So there are many groups looking at different approaches to address the surface attributes. I spoke a little bit about laser. There are guys who do so-called laser finishing or texturing to try and remove, reduce this kind of roughness. There is some tribo finishing as well. Sorry for the typo here, but there is, this is also done by several groups. I want to talk a little bit about chemical etching and electrochemical polishing, yeah, because these are becoming more and more attractive for at least the gas turbine guys, yeah. And what we do by Hertization is essentially a variant of chemical polishing or electrochemical polishing. This is another example. Just roll it with abrasive media, get substantial improvement sequentially in roughness. You can see you get a lousy part to start with lousy looking, but near net shape, yeah, and then you want to remove the roughness, yeah. Um, we spoke about techniques that do not remove material, and short peening is one of the more prominent ones, works very well. So you have so-called shots. The shots can be made of anything. Yeah, it could be stainless steel, it could be glass beads, depending upon what is the material you want to treat. Yeah, you can do short peening and get substantial improvement uh, in the surface attributes. You also can get significant grain refinement at the surface by short peening, right. So, all of these are very widely practiced uh, in the industry, at least the short peening part. This again a regime of significant research interest using laser to polish, yeah, and you can get uh, uh, fairly good surface finish. There's something I must say here, right? I mean, uh, we have a tendency to believe that laser is very expensive, yeah, and laser is very slow, yeah. But things have changed a lot over recent times. You can raster a laser at unbelievable speed, right? And that's one of the reasons why something like this has become very important. I have a collaborator in Poland right now and also in the Czech Republic. They do this kind of work. So we have just sent them samples to be able to laser polish, and they cover large areas in less than a minute, you know. So there are these days gantries that traverse a laser at speeds which are unbelievable, and you don't need so much power, right? You're not doing great deal of processing in that sense. So with the evolution of new lasers, this has become more practical now, yeah, and affordable as well to be commercially interesting, right? Little bit about chemical and electrochemical polishing and what is the heart of hertization here. Yeah, chemical polishing very cost effective, relatively simple. It's just like etching. Yeah, if you are familiar with etching, it's just like that. Electrochemical can give a finish which is even better than the chemical approach. It can effectively reach areas which appear inaccessible because you are dipping it in, yeah, and of course for anything which is good you need to pay a price. So it's more expensive than this, but worthwhile for many parts where the the geometry is very complex and there are intricate features that cannot be left unfinished, so to speak, right? So that's a way to go. So this is one of the recent equipments that we have got. Yeah. Say that again. Very good question. Yeah, I mean, it's not so well studied, but it is almost like over etching, right? And I think that's why you are asking the question, right? If you over etch, yeah, you will not get the surface that you want. So there is a lot of optimization involved there. So although I don't have data on it, I am convinced that if you don't do this part right, you will not get such a great surface, yeah, or maybe you will even get a worse surface than before. So you need to optimize, yeah. Yeah, correct. What is? It does refine the grains quite a bit. As it's almost similar to this, right? You see a big difference in the extent of refinement. You do see that, yeah. And again, there are everything is almost a science, right? I mean, you can call it bead blasting, but there are many variables in this. Yeah, at what velocity do you blast? What compressed air pressure do you use? What is the shot size? What is the material of the shot? Right? All of these make difference. So, but as you can see here, you clearly get substantial grain refinement, right? And the other thing which is not shown here is some of the residual stresses that we are talking about. Even those are alleviated during this process. So, yeah, quite a few benefits actually. But let's come to this. So, this is a new equipment for hertization that has been set up by one of the institutes which is not next door to us, but pretty close. Yeah, and it uses a pulsed current to control this electrochemical process of surface polishing. Yeah, and just imagine this costs almost close to several $100,000, and people are investing in this just, I mean, it's easy to say just to surface finish a built component, right? But that also tells you both things, the fact that someone will develop an equipment like this and the fact that someone will buy an equipment like this. Yeah, both of these tell you that this is a very crucial step in making an AM built part worthy of final use, right? We were talking about intricate geometry. Let's say cooling hole for example. If that is not properly finished, then it disturbs the dynamics of gas flow inside those holes. I mean, there are lots of implications, right? And that's why people don't mind investing in something as expensive and as complicated looking as this. I mean, once you optimize it, is of course not so complicated, but until then, right? Very quickly, this hertization process then embraces both chemical and electrochemical routes for surface modification. I have seen this system. It lends itself completely to full automation, but there is a long optimization protocol. For every chemistry, you need to do everything different, right from the bath composition to the time for which you do it, everything is different, but it's very interesting, and it of course is suitable for all printing methods. I don't know why they advertise it like this, because it's obvious it is material specific, not process specific, but all these marketing guys write all sorts of stuff. But yeah, so if you have, for example, Inconel 718, there will be a certain protocol. If you have stainless steel, it will be something else. If it is a nickel based superalloy, which is slightly different, like Hinge 282 instead of Inconel, it will still be different, right? There are several challenges to overcome, including removal of support structure. This can do that as well. Treating internal channels like cooling holes. There are instances where, especially in these intricate geometries, there is loose powder on the inside, which has not gotten off fully when you grid blast, right? So it takes care of that as well, right? So, so in a sense, it encompasses what all these things try to do. At least that's the claim. I don't have, I'm not rich enough to get that equipment, but they claim this can do everything that tumbling does, laser polishing does, electro polishing, blasting. All of it can be done by this machine, kind of, right? So several steps going through this. One is support removal and just initial cleaning. Imagine yourself going through a very sophisticated electroplating setup. I don't know how many of you have seen a electroplating setup, right? It goes through various stages of cleaning, or even PVD, right? So it's something like that. First step, initial cleaning, which is quite intricate actually, but it ensures that the surface is absolutely clean. The next step is what leads to a reduction in surface roughness because of chemical and electrochemical etching, and then if you want to go beyond that, this step is optional, but then you can get a very fine polishing on the surface. As you can imagine, this is a very slow process. Yeah. On the flip side, you can load multiple parts in the bath at the same time, but it's a slow process because you are removing the roughness by etching. So it takes a while, but you can eventually get almost a mirror finish. I've seen this happen. So something new to keep your eyes open for. Yeah. So what do you consider when you do hertization? Well, biggest challenge. Even if I send a small coupon to do this, Swati will tell me, make sure there is a hole in your part, right? Because it needs to be hung. Yeah, you need to find a good way of hanging that, right? And there are other issues, not challenges in the sense, but yeah, you need to take all of these into account, and then also be very sure about what do you eventually need, right? You don't want to run this equipment for a long time if that level of surface finish is not necessary, right? So you should be clear about what your requirement is, but very exciting process to achieve what you want, right? As printed part, pretty rough. Step 1, which is essentially cleaning, and then step 2 looks pretty good, and then you can almost make it very nice. Some example that from what Swati is doing at the moment on an aluminum alloy with hertization, and then yeah, she's going through this process of optimizing this hertization protocol for polishing this, and yeah, so this is the starting morphology of the aluminum built alloy, and then you get much refined surface, yeah, right? This is the same magnification on the left, yeah, much smoother surface, so it's very good. And then if you take it even further, this is all by chemical etching. You have just dipped the bath and turning some knobs, and very good, very impressive to do that. Yeah. Before I move on to thermal post treatment, any questions? Yes, please. It's available with an institute like ARCI here. There is an institute called RICE, and they can afford it because they have some 150 companies as contributing partners in that institute, and several of them are interested in AM. So what the institute sets up is decided by a board which has these industry guys as partners. So they've been asked to look at hertization, but yeah, I know them, so I get some stuff done. But otherwise, this is something very nice. Yes. Which material? But I mean, they've been working on all sorts of things. I know. Yeah. I don't remember, but on this, if you need more data, just write to me, or if you have questions, I can get them from the people who are already using it. So yeah. So this is a more involved aspect than surface treatment. Thermal post processing, yeah, is you don't need it for all AM build parts, right? But for some AM build parts, especially super alloys, etc., this is inevitable, right? and what you need is eventually governed by what the end application is, right? Uh, so what I'm going to try and do is talk a little bit about why do you need thermal post treatment, under what circumstances, yeah? What are the different types of post treatment, thermal post treatment? I won't go too much into parameters for post treatment, but I'll give you some flavor, especially when it comes to temperature. Yeah, what happens if you post treat at a very high temperature, right? When does grain coarsening begin to happen? You don't want that, and then assess impact of these post treatments, especially on mechanical properties, because more often than not, that is what is the driver for thermal post treatment. Functional performance, not surface attributes, right? So, we will talk about that. So, motivation for thermal post treatment, I can give many reasons. One is defects. Doesn't matter how much you optimize your AM process, there are defects which are going to be inevitable, right? Some applications can live with those defects, some applications cannot live with those defects, right? But defects, what can be those defects? That could be porosity. The source of this porosity can be anything. It could be shrinkage porosity, it could be lack of fusion, it could be something that we discussed in the morning, originating from your feedstock, yeah, because so all of these, depending on application, something like this can be a reason for doing post treatment. Sometimes it could be non-uniformity, right? If we build a part like this, for example, we find that the face constitution is little bit different, yeah, at different location, because all of them have seen, each location has seen a different thermal history, right? Why has each location seen a different thermal history? I must explain a little bit more. Imagine that this part is built by EBM, yeah. Why has this location seen different thermal history, all of them? Why should there be a change in phases? Anyone? Yeah? Correct. Your first answer is correct. Now you should not make life difficult for yourself. Your first answer was perfect. Now you are talking about heat affected zone and diffusion zone. Now I will ask you to explain. Please explain. Yeah. So far you are correct, right? So for example, imagine that you start building, yeah? It's EBM, your bed temperature is 1000 degrees, right? And this is taking you 6-7 hours to build, right? So this part has seen 1000 degrees for 6 or 7 hours, yeah? This has seen it for 4 hours, 3 hours, 2 hours, yeah? Enough. That is enough to cause a phase change, right? Let's not talk about heat affected zone and make it too complicated, right? Because for that reason the temperature history is different, and therefore the phase constitution in each layer can be non-uniform, right? And you may therefore require a thermal post treatment to nullify this non-uniformity. What else, right? You may want certain strengthening phases in your build structure. Many of the superalloys are precipitation strengthened superalloys, right? And therefore you may want to ensure that this kind of precipitation happens in the part before you build it, right? So that could be one of the reasons. How many of you have heard of Lave's phases? Anyone? Anyone has worked with superalloys? Yeah. But in any case, then believe me that these kind of Lave's phases form in many nickel based superalloys, and these are usually detrimental from a mechanical property standpoint, and you want to get rid of that, right. So, that could be one of the reasons for post treatment. We spoke little bit about anisotropy, yeah, in the build direction and in the direction transverse to that. Uh, uh, so, this kind of post treatment also meant to address issues of anisotropy. And finally, residual stress, more in case of EBM, slightly less in case of SLM, but there are parts when residual stresses are of course high and undesirable. So, you may want to post treat to alleviate those stresses, right. So, let us look at what kind of thermal post treatments can you carry out. One is you can do it at low pressure, or you can do it at ambient pressure, or you can do it at high pressure. Generally, low pressure treatments can be done in a controlled atmosphere, as indeed these ambient pressure also. If it is low pressure, it is vacuum. If it is ambient pressure, you can use argon or something like that, yeah, to do the heat treatment or thermal post treatment. And you can do it at high pressure, which is like hot isostatic pressing, yeah. We will come to that in a little bit. But do remember that these thermal post treatments are integral to improving the mechanical performance of the part, and therefore, for most high performance applications it is unavoidable, correct, and therefore, you must have a good idea of how the mechanical properties are improved, and in the process you should be able to control the microstructure, because that is what will govern the mechanical properties, right. So, in that sense very complex compared to surface post treatment. Thermal post treatment is very complicated, takes a long time for it to be investigated, and therefore, even longer time later for it to be qualified by the user and put in practice, right. So, two prominent approaches, one involves hot isostatic pressing, the other involves in one sense traditional heat treatment. Let us talk about hot isostatic pressing. It involves as the name suggests, it involves pressing at high temperature, yeah, and also at high pressure. The typical gas pressure can be varied over a fairly wide range. Usually, you see equipment that goes from 35 to 200 megapascal, and you can of course vary the temperature also over a fairly wide window, of course always below melting for sure, but as a thumb rule it is good practice to do this at about 0.7 times the melting temperature, yeah. So, we've done this heat treatment over almost this entire pressure range. We have done it at different temperatures as well. We have a good partner in a company called Quintus. I don't know how many of you have heard of Quintus, but it's one of the leading manufacturers of HIP equipment today, right? And then we've been fortunate to be able to do all our hipping in their systems in Sweden. Let me see if you can hear what is being said, but
the more complex the technology, the more important to focus on the details. We must minimize the risk of inconsistencies in our materials in order to be able to take product quality for granted. Materials formed from casting or additive methods.
I'm showing it for two reasons. One is because it's a very important step in thermal post treatment. And second, I want to be nice to them because they have been very nice to me in in running all my experiments. So
Methods such as 3D printing contain porosities or microcavities. These porosities must be reduced to eliminate the risk of premature breakage. This is usually done in 2 steps. Firstly, heat is applied under pressure in a HIP process which reduces porosities and cavities. Secondly, the material is heat treated in a process where rapid cooling improves the fatigue and ductile properties. It would be a big advantage if these processes could be combined to save energy and increase productivity. But combining quick cooling with high pressure places stringent demands on the pressurized furnace. The vessel needs to be robust enough to withstand the high pressure while also being cooled quickly from the outside. By adding a wire package to the outside of the vessel, both can be achieved. The wire package allows the inner wall to be thinner for quicker cooling, with maintained structural integrity of the pressure vessel. The thinner wall enables a unique heat exchange system, which makes it possible to cool down the load quickly and meet the requirements of the heat treatment process. This means that the HIP process and the heat treatment can be run at the same time in the same vessel, saving time and energy. Through the Quintis Uniform Rapid Cooling System, URC, the hot gas is pushed towards the thin-walled vessel. At the same time, the vessel wall is cooled by water from the outside, while it is supported by the wire package to keep it safe and under control throughout the process. With this unique combination of HIP and heat treatment in one, the load only needs to be heated and cooled once. This gives significant savings in productivity and energy costs. In addition, continuous cooling under pressure reduces tension and the risk of future material breakage. Combining the 2 processes also saves space, reduces the need for process infrastructure, and cuts equipment investment costs. When looking at HIP and heat treatment to improve material properties, safety, capacity, and energy cost are important factors regarding both the investment and the operation. Combining the processes offers many benefits and enables more components and details to be treated in a way that ensures they will perform the way we expect. Quintis, the global leader in high-pressure technology.
So I hope that gave you some insight into what hipping is all about and what it can do. But oops. Having seen how it works, I must say that there are 3 key parameters: temperature, time, pressure, and all of them mean money, especially time, right? So you're always trying to reduce the time for pre-treatment, and since we have worked so closely with these guys, they use many of our results for their marketing now to the AM community. So yeah, so typical goals. HIP is not new. HIP has not been developed for AM. That you must understand. HIP technology is fairly old, and the typical goals for using HIP have been to, of course, always get better mechanical properties, produce the final product by the powder metallurgy route, right? I mean, there are enough hipping equipments actually in India itself, yeah. But so we are now using this existing technology, which has been especially in vogue for powder metallurgy components, and now you want to use it for additively manufactured parts to both enhance properties and eliminate defects, right? The driver for that is essentially to remove defects. That's what hipping really does. yeah, remove pore defects, and therefore lead to augmentation of all sorts of mechanical properties, whether it is yield and tensile strength, ductility, much improved, fatigue life. This is what our results have shown so far. And also equally important is the fact that it reduces or eliminates rejects because of defects and things like that. Yeah. I don't. Something I want to emphasize here, what we mentioned yesterday, that the open pores cannot be healed by hipping, only closed pores can be healed. Yeah, and I will leave it at that now. Maybe when there is, maybe I talk about it now. Yeah, why are open pores not healed? Anyone? What's the problem with open to surface pores or defects? Why does hipping not deal with those in a good way?
There's a risk of breakage.
Risk of breakage.
Can reduce the strength of the material.
Open to surface. Yeah. So it could just be something like a cavity on top. It could be interconnected porosity which goes inside, but is eventually open to the surface. Those kind of pores hipping cannot close. Yeah, those kind of defects. Why do you think that is the case? No, it's simply because then if it's open, then the application of pressure has no impact on the microstructure because it's open, right? So, on the other hand, if it is closed, then application of pressure and temperature can heal that defect. Correct, right? So, one of the things we have been trying to do, I don't think I have any slides on that. One of the things we have been trying to do is see if we can coat the part and then hip. Yeah. So, if there is an open to surface porosity, then it becomes closed porosity because of the coating. The other alternative, of course, is encapsulation. I didn't talk so much about that, but in hip many times you encapsulate the part and then hip, right? But that is impractical for many large aero engine parts. You cannot encapsulate the part, but many of these parts could require coatings eventually for surface protection or whatever reason. So, one of the projects we are dealing with is, can we coat first and then hip, so that the coating itself will serve as an encapsulation and therefore not have open to surface porosities. Unless they are present in the coating, then that doesn't help, right? So, that's one of the things we have been looking at. So, influence of heat treatment on porosity, what I am trying to show is couple of things. Yeah, one is conventional heat treatment at 1120 and 1185 degrees. This is as built. So, if you do conventional heat treatment, it does nothing to the porosity, right? But if we do hipping, it reduces the porosity quite a bit. Why 1120 and 1185, you may ask? These are crazy temperatures. I was talking yesterday about standards, right? There are standards for wrought and cast 718, yeah, that talk about heat treatment in the temperature range 1120 to 1185. So, we decided that we would heat treat at the two limits of that range, because the standard says 1120 to 1185, right? But the message here is no densification happens in conventional heat treatment. All the densification happens only in a hip, right? This is another example of how hipping can very nicely get rid of defects, right? As it is, if you do your AM well, there is not so much porosity, right? I mean, this is an expanded scale, we are only talking about 0.7 volume percent defects. That's not much, but that's not much depends upon what's the application. If you're talking about aerospace, they will say that's a lot, right? We can't deal with that, yeah, especially for some rotating parts, etc. We don't want 0.7%. In that case, this becomes unavoidable. Then we do HIP, right? But the take-home message is that HIP extremely effective to get rid of any kinds of pores and defects, right? Let's take that little bit further, right? I mean, as I told you, these are the two limits of the temperature over which which is specified in the standard for traditional 718. So, we have done this hipping at two different temperatures, 1120 and 1185, and you can see here, yeah, slightly better properties for 1120 actually, right? But in both cases you get almost full densification. I don't know if I have, maybe I don't have, I don't have data here for microstructure, but as a part of this study by Sneha, we realized that at 1185 you begin to see coarsening of the grains, right? So, most of our work then we restricted to 1120 degrees hipping, right? So, the next question which came to our mind is, if you are going to hip anyway, yeah, and certain applications make hip unavoidable. So, if you are going to hip in any case, how does it matter how you have built it, right? Is that a good logic? Suppose the application requires me to hip, then why should I worry about optimizing my EBM parameters, for example, to get a very good build? How do I care? Because I am going to hip it later. Is that a good argument? It's a lousy argument, or?
It's not a good argument.
It's not a good argument. Why?
Because more we get the defects, the more weaker the material is. Even if we not hip also, even we think that it's just a minor thing and we hip it, but depends, that structure is depend on the strength of the material. The more we get, the more weaker it is.
But you are not going to determine strength in as-built condition. You are going to eventually hip, right?
But that hipping process is the secondary. The first, the material should be clear or the stronger.
Why?
Other applications now.
No. You are doing hipping, all thermal treatment you are doing, so that you eventually get mechanical properties that are of interest to you. You don't care what your as-built thing looks like, right? That's the reason you want to post treat.
Phases that are formed will not happen due to probably in as-built condition only the required phases are formed.
In as-built condition. But after that it is going to see all sorts of thermal treatment.
But the parent phase required may not be formed.
Which I can guarantee will not form anyway. Yeah, if you look at a nickel-based superalloy, if you look at how it is put to use, it has to be solutionized, it has to be double-edged, yeah, to get the precipitates that we spoke about, right? So, all that action is going to happen later anyway, right? And that doesn't happen in as-built condition. Yeah, when you do EBM or SLM of a superalloy, you don't get a phase constitution that you want. As I showed in the motivation, in fact, you get some Laves phases and things like that, which you must get rid of, right? So, in particular, let me refine that question better. If there is a way for me to EBM build faster, right, and doesn't matter if instead of 0.7% porosity, I get 5% porosity, yeah, but it allows me to build very fast, yeah, then is it a good idea if I am going to hip? That I build fast and then I hip and do something like that. Yeah? If we don't have an answer, we also didn't have an answer. We were looking for an answer. Yeah. So, we constructed this experiment, right. So, we intentionally built in ABM, in an EBM, samples with very different porosity. Yeah. We intentionally introduced defects. There are many ways to introduce defects intentionally while you are processing. What we did in this case was only change the melting speed, right. All other process parameters same, we change the melting speed. And then what happens? We get very lousy microstructures, right, very bad, because you are building it very fast, right. This is scanning speed, right. So, if you go from 0.6 to 1.8, you are building it 3 times faster. Yeah. Else is same, you are building it 3 times faster. Yeah. And if you build 3 times faster, as you expect, you get horrible microstructures. Yeah. But in this case, they are intentionally produced. We have produced those defects ourselves on purpose, right. So, initial as built under normal cases 0.5 to 0.7 that I showed you earlier. If you build little bit faster, 2.7% defects. If you build it very fast, 17% defects, and then we hip it. Yeah. Voila, everything gone, right. And that is what we wanted to try and show, that this is little bit tricky, but you must understand. We could do it in this case because we are targeting applications which absolutely make hipping mandatory. Not all applications require that, right. So, this is only for cases where you already know that you are going to hip, right, because the application cannot allow you to put that part in application without hipping. And because we know that we are going to hip eventually, then you can think of a strategy like this. Yeah. But if there are applications that do not absolutely demand hipping, then this is a bad strategy, because then it forces you to hip. Yeah. That is not what you want to do, correct. Then you are better off building it like this, because that application may be okay with 0.5, 0.7, correct. So, you need to be little bit careful in what you decide. What looks like a great idea here may not be a great idea for some other application, correct. But this for us was very promising, right. So, this is the question we were asking, that if you are going to hip in any case, can you build faster? And looks like the answer is yes, yeah? At least based on these studies, but this is just microstructure. So, we did several things after that. We exposed this to high temperature. How many of you have heard of thermally induced porosity, right? You have heard of thermally induced porosity, right? So, that can happen. It can look like a nice microstructure, but when you expose it to temperature, it can open up again, yeah, and give you porosity. But we tried it in that case and didn't happen. But when does HIP not do its job? So, there were very few little dots here you see, yeah. So, we were trying to see what is going on there. So, we found that the only places where hipping does not densify is those where there is some inclusion, right. So, related to the feedstock, right. Very high magnification here. So, this scale is about 9 microns or something. So, we find that wherever there is some oxide inclusion, that is where it does not successfully hip, but otherwise it densifies everywhere. Yeah. Influence on build properties, you should always keep an eye on microstructure, one. Yeah. Then you must look at it deeper. For example, here everything looks nice, right. Everything looks dense. Here it looks dense, here it looks dense, right. But then you go one step further, look at it one more time, right. 1120 degrees. So, this is, we spoke about contour and hatch yesterday, contour and then hatch in between. So, this is the microstructure in the contour, slightly different than in the hatch, because we use different parameters. Yeah. This is after hipping at 1120 degrees. This is after hipping the same sample at 1185. Yeah. So you begin to see grain coarsening now. Yeah. Everything else same pressure, same duration, different temperature. You see grain coarsening, and this is something you don't want. So although your pore healing is effective or defects are gone, you don't want grain coarsening, correct? So that's how we decide on using 1120 then, right? So grain growth during hipping is something that you want to avoid, right? We've looked at this aspect in great detail. We have also begun to look at how different AM processes respond to hipping. So we've looked at, for example, EBM and SLM. And we find that there is more grain coarsening in case of SLM for some reason. You also see a structure that is very different. Yeah. In one case, you have a columnar structure. In another case, at least when you start, you have an equiax structure. Correct. So it's good for you to know that these things can happen, right? And then we have intentionally, just like we intentionally tailored defects, we intentionally tailored microstructure while building high aspect ratio columnar, low aspect ratio columnar, mixed columnar with equiaxed, fully equiaxed. And we always found that if we had equiaxed, the grain coarsening was much more, yeah, in the sample. So you can play around quite a bit with this, but important to know what goes on, right? Effect of hip on these phases, delta and gamma double prime. That's also we investigated a lot, and then we found that if you hip it under the right conditions, it can dissolve the delta and gamma prime phases and lead to a much more homogeneous matrix, as you can see here. So not only are the defects gone, these kind of phases are also effectively taken care of during hipping, right? What else? We spoke about inclusions. So if you have inclusions such as alumina or titanium nitride, yeah, which come from the feedstock, yeah, hipping does nothing to them, right? So they are retained even at the end of hipping. So hipping gets rid of pores and defects, but it does nothing to the inclusions, right? So that's the message, correct? Any questions about hipping? Yeah, because when you do thermal post treatment, hipping is the first step, right? Where you are essentially getting rid of defects and pores, yeah, and to some extent ensuring that your delta phase, etc., is gone. But even if that didn't happen, that is the purpose of carrying out the heat treatment later. So the main motivation for hipping is defect closure, right? Nothing more. So any questions about that, or can we talk about heat treatment then? So let's talk about heat treatment. Yeah. No. I'm saying that again and again. It is not it's not to be used for all applications. It's an expensive step. Yeah. It's an expensive step. So you don't, if you can avoid hipping, you don't want to hip. Yeah. And I want everyone to be clear about that. You don't want to combine two expensive processes. AM itself is expensive. You don't want to combine it with HIP. And HIP also is a very sophisticated equipment. Most companies will not have HIP. They will send their parts out to some facility where it can be hipped. Yeah. So hipping is to be avoided if your application allows you to avoid it, correct? So we are asking ourselves the exact opposite question, right? That if you know that you have to hip because your airworthiness certification demands hipping, then what can you do, right? So, everything that I showed you so far is assuming that you cannot do without hipping, and then what happens if you do it at 1120 degrees, 1185 degrees, if you do it on a good build, bad build, yeah. But for that, the answer to this question, do I need to hip, should be clear at the beginning, right?
What is the simplest thermal heat treatment of an AM product so that we can enhance the product?
That's a don't take it personal, but that's a bad question to ask. Yeah, why? Because it depends upon what material you are building it from, yeah, and what is the application. So, if you say if I have done my build in stainless steel, yeah, I may say, no, why are you heat treating? I will ask you the question. If it is Inconel 718, I will tell you a certain treatment which I am going to talk about. But if you are talking about Haynes 282 or TI 64, what I talk about will not be relevant. Something else may be relevant, right? So, there is nothing like an ideal heat treatment. You must understand that it is material specific. Yeah. So, let's talk about that, and then if you still have that question, we will talk about that more. Yeah. So, let's talk about conventional heat treatment and its relevance to AM. So, you know what heat treatment is, right? Yeah. You take the material to a certain temperature, hold it for a specific predetermined duration, and then cool it. You can change various things here. Yeah. So, the real money is in knowing how to heat treat, right? It could involve various things. At what rate do you heat it up? Yeah. At what temperature do you hold, and for how long, and at what rate you cool down. All of them are important depending upon material, right? And therefore, it is crucial that you understand for your material system what it should look like, right? Let's start off for what is often the most basic step for heat treatment, right? And this could be true irrespective of material many times. Yeah. Imagine that you have lot of residual stresses in your part, yeah, which is usually true in case of laser beam powder bed, also true to some extent in case of DED, and then it is very common to perform a stress relieving heat treatment, yeah, at whatever condition is appropriate for that material, correct? Yeah. So, they are usually at a reasonable temperature and time, but if you do that, you can see how it looks like after you heat treat. There is a substantial alleviation of stresses, and that is what you must accomplish. The same thing that I showed you for hipping still holds. Your time and temperature should be such that you avoid grain growth and recrystallization. You do not want that to happen, but you want to relieve the stresses, right. So, therefore, this may require some optimization for the material that is of interest to you, right. So, if you ask me from an AM perspective, what kind of heat treatments are relevant, I think this is almost commonly used stress relieving heat treatment that we quickly spoke about. I talk about that again and again. You do not want grain coarsening because that will adversely influence your mechanical properties. The other kinds of heat treatments, these two are very material specific, and I am going to today give you examples that are related to Inconel 718. Yeah. But they will be applicable to many other super alloys. Yeah, one of them is solutionizing treatment, also known as solution annealing or homogenization, right, where the idea is to ensure that any elemental segregation that has happened during building is nullified, Yeah, you want to dissolve undesired phases like Lave's and delta phase that I spoke about, and kind of prepare the material for aging which follows, right. So, that is the purpose of your solution treatment, and then the aging, it depends upon material, but the intent is to ensure that all these strengthening precipitates appear, yeah, uh, through suitable heat treatment, so that your mechanical properties are improved. Do you want to watch a video? We have time, right? Yeah. So, let us look at that, because I think this is important. Uh, it's important if it works.
Hey guys, welcome to SkillLink. We are surrounded by a large number of objects, and each object has its own properties. In one of our previous videos, we saw different types of crystal structures that contribute to the properties of the materials. But there, we've covered only the structures of solids made of a single type of atom, in other words, pure substances. In reality, almost every object has impurities in it. Sometimes, impurities are also added to the substances intentionally for improving their properties. One such addition of impurities to other substances yields solid solution, and that is what we're going to discuss today. We'll be discussing what solid solutions are, why do we need to study them, and the types of solid solution and the rules governing them. Let's start with what an alloy is. An alloy is a mixture of metals formed by adding a certain amount of metals, called alloying metals, into another metal called the base metal. This is usually done for obtaining the desired properties. For example, pure silver is anti-corrosive, but it is also very soft. Adding a certain amount of copper to silver forms an alloy called sterling silver. This improves the mechanical properties without affecting its anti-corrosiveness. Alloys can be divided into two types. They are solid solutions and intermetallic compounds. A solid solution is a solid-state mixture that contains two or more solutes in a solvent. A solid solution consists of a single phase throughout, and the crystal structure of the solvent remains unchanged even after adding the solute. Whereas, when the crystal structure of the alloy is different from its constituents, then it is said to be an intermetallic compound. Another major difference between these two is that the composition of the intermetallic compound is fixed, whereas the composition of the constituents in a solid solution may vary. For example, a copper and nickel solid solution may contain different combinations of copper and nickel. But why do we need to study them? As mentioned, adding a metal into another changes its property. The property of the alloy changes according to the composition. Therefore, for selecting a material for a desired application, one should know the concentration of the metals, which shows the required properties. Now, let's move on to see the different types of solid solutions. Based on the location occupied by the solute atoms, solid solutions are divided into two types. They are interstitial solid solutions and substitutional solid solutions. If the solute atoms occupy the interstitial space, that is the space between the solvent atoms, then the solution is said to be interstitial. On the other hand, if the solute atoms replace some solvent atoms and take their place, then it is said to be a substitutional solution. Substitutional solid solution can be further classified into two types, namely ordered solid solution and disordered solid solution. In an ordered solid solution, the solute atoms take a fixed position among the solvent atoms and are arranged in an orderly manner. Then it is said to be an ordered solid solution. This type is seen in aluminum-copper solid solution, where the aluminum atoms occupy the corner position and the copper atoms occupy the face-centered position. If the solute atoms occupy random positions in the crystal lattice, then we call it a disordered solid solution. Most of the solid solutions are of this type. Well, that's all about the types. But do all elements form solid solutions? The elements should possess some similar properties to form solid solutions. Kuhn-Rothery put forth a certain set of rules that state the conditions for metals to form solid solutions. First, both the solute and solvent atoms should have similar atomic radius. The difference between the radii of the atoms must be less than 15% so that they form a solid solution. Then, both the atoms have similar crystal structure, which favors the formation of solid solution. Next, the electronegativities, that is, the nature of the atoms to attract electrons, should be the same. And last, they should have the same valency. Well, that's all we're going to discuss in this particular video.
Actually, I wanted to show this so that I could sit down for. We do solution treatment essentially to take care of that, and then aging. Yeah, there are specific aging protocols. There are in fact standards available. Yeah, of how you age. I should have put that standard here, but no matter. If you are looking at wrought or cast Inconel 718, it calls for a solution treatment which is, I think, 1 hour and 15 minutes long. Yeah, and then it has a 2-step aging, which is 8 hours plus 8 hours. So, can you imagine, you are doing almost 20 hours of heat treatment, including heating and cooling, to eventually get what you have built in a form that is usable. 20 hours, right? So again, little bit of the same solution treatment to dissolve unwanted phases, aging to form and grow precipitates of interest. Yeah, and Inconel 718 is a precipitation strengthened superalloy, right? And that's the reason why you have the kind of aging treatments like I specified just now. Yeah. Oh, I thought I didn't put the standard, but looks like I have, right? So if you look at the standard out there, which is specified for powder bed fusion, yeah, there are all these numbers for the standards. They involve a solution treatment in this range, yeah, 927 to 1010 degrees for 1 or 2 hours, followed by either water quenching or air cooling, and then they involve a 2-step aging. 8 hours at about 720 degrees, another 8 hours at 621 degrees, total time of 18 hours. Yeah, so that's a standard for you to get what precipitates you want. So we've done various things. We have taken an as-built specimen and done all that. We have taken a HIP specimen and done all that. Yeah, and then we have also in both of these cases stopped specimens at that stage, and at that stage, correct, to see what's happening. Our real objective was to also answer the question, do we really need 18 hours, right? Maybe it's in the standard for a wrought or cast material, but in an AM material, do you need 18 hours, right? So those were some of the questions we were trying to ask, and therefore, to answer that question, we said let's break this up. Yeah, for example, the solution treatment, 1 to 2 hours is specified, but let's see what happens after 15 minutes, half an hour. Yeah, at various intervals, even for aging. Let's look at 1, 4, and 8 and see if it makes sense for us to stop any of these treatments at some level, right? Thinking that we have already accomplished what was meant to be accomplished as per this standard, right? So that was the motivation. So just some quick results for you, right? So this is as built with delta phase decorating the grain boundary, right, in an Inconel 718, and this is without prior hipping, but we did it for 15 minutes, 30 minutes, 45, 60, right. in both of these cases, and then you see that you begin to see these kind of grain boundaries at I mean delta phase decoration at about 45 minutes, right? But not big difference between 45 minutes and what's in the standard. So, no great motivation to look at solution treatment further, right? Let's look at aging, right? You want to age it just right. So you want to perform what is kind of called as peak aging, right? To get the right kind of mechanical properties. You don't want to underage, you don't want to overage, because on either side of peak aging you begin to compromise the mechanical properties, right? And that's the reason we wanted to investigate this at various instances. So, these are some of the micrographs at various stages. This is almost at the beginning, where you have a super saturated solid solution. This is showing some strengthening precipitates, but small, tiny, so reflective of underaging. This is when we do it for too long and get very coarse precipitates, right? So, we were trying to hit this particular peak aging condition, right, and that was the motivation. As you know, precipitation happens because of supersaturation, and that's a condition you need to reach, right. Once again, as a reminder, the idea was to try and shorten the post-treatment protocol, because that is what costs money there, right. So, this is a summary of everything that happens during aging from the samples that we were looking at. So, this is a hip sample, this is an as-built specimen. After hipping, you actually see a drop in hardness, because it has homogenized. Whatever other undesirable phases were there have vanished, and you get the same effect as you get during hipping, during solution treatment. But what is interesting is what happens during aging. The first step of aging, 1 hour, 4 hours, 8 hours, and then second step of aging, 1 hour, 4 hours and 8 hours, right. So, our argument then was that you've already accomplished what you needed, so not much difference there. So, can we stop this after 4 hours, right? Here you have achieved this right after 1 hour, so can you stop it after 1 hour, right? So, can you convert your aging, two-step aging, from 8 plus 8 hours to 4 plus 1 hour, right, and shrink that, because that is a substantial reduction if you can go from 18, 20 hours to 5 hours, right. So, most of what I show you now is to impress upon you that you can shorten these heat treatments, right. So, this is evolution during aging, 1, 4, 8 during stage 1, and then 8 plus 1 and 8 plus 4, right, during. So, we've looked at all that, and then we think 4 plus 1 looks pretty good in terms of precipitation compared to the current standard, which is 8 plus 8, right. So, so that is one way in which, for any given material that you are interested in, take a look at whether the existing recommended thermal post treatments are appropriate, or is there room to make big changes in what is presented as a standard at the present time. Yeah. So, we are at the moment we are in a state of flux, because it is still new AM. So, people are borrowing standards which have existed for a long time. Yeah. So, same standard for cast and wrought 718 continues to be passed off as standard for AM built 718, and that is perhaps true for all other super alloys and things like that as well. So, so just a quick summary on what is accomplished by these thermal post treatments very quickly. Defects, we saw that HIP will eliminate defects, but simple heat treatment will have no effect, nothing will happen. If you are looking at inclusions, neither heat treatment nor HIPping makes any changes to the inclusions. Same with the carbides. Hardness directly correlated to the strengthening phase, the gamma double prime, right. It depends upon how your gamma double prime evolves. Yeah. Speaking of which, the gamma double prime, you see that it completely dissolves during HIPping and also during solution treatment. That's why you see a drop in hardness, if you remember. Yeah. And then it precipitates, of course, during aging, right. So, the heat treatments have an influence on all of these, right, including not the least the grain size. We saw that even between 1120 and 1185, there is a big difference in grain size, correct. So, and you do not want that kind of coarsening to happen, right. So, the takeaway message for me is that the standards which currently were existing for standard wrought or cast materials may not be ideal for AM. They will work for AM, but I think you do not need to spend so much money to do a 20-hour cycle when you can do it in 5 hours, right. I have only showed you microstructures and things like that, but where is the proof? Yeah, because eventually you want to see mechanical properties. So, we have tried to do this at different levels. We have looked at ductility and tried to compare. I mean, this is irrelevant what as built looks like, but you really want to compare how does the 4+1 cycle compare with the 8+8 cycle, right. So, we have done it for ductility, looks pretty good. We have done it for the ultimate tensile strength, looks nice, not very different. So, it seems like everything plateaus kind of at 4+1, right. This is another way of presenting the same thing from different builds. So, we wanted to be sure that the way you build is not influencing our data. So, these are same material built at different times in different equipment, and we are then trying to compare how this looks like, right. So, looks quite nice. We have been using this kind of an equipment for HIPping. The reason I showed you that video from Quintus is now this equipment allows us to do not just HIPping, but HIPping plus solutionizing plus aging in the same furnace, right. So, our next ambition was that can we do this 4+1 cycle inside HIP, because we are HIPping it in any case, right. So, we that is what we began to explore, because this facility provides us that possibility during the because of the ultra rapid cooling or quenching that is possible in their furnaces. So, we thought let us try and program this in the following manner, right. Combine the HIP plus heat and solution heat treatment, age it here, and do it all in a single program, because most companies like to see that. Certainly, the two gas turbine manufacturers who are our partners, because it leads to direct saving in lead time, cost, because you need to ship it out for HIPping in any case. So, do everything there, right, inside the HIP. So, this then is our constructed cycle. This is the standard solutionizing for an hour 8+8, and then this is what we decided to do inside the furnace, right. So, HIP it, cool it, take it to solution treatment, do 4+1, and what goes in comes off here. So, this is a truncated thermal treatment cycle in one sense, right. and super good actually. This is with the shortened heat treatment done inside the hip, yeah, by combining that. So, I think this is a great result for us. Now we are also getting a little bit greedy, trying to see, do we even need solution treatment if you are going to hip at 11-20 degrees for an hour? Can we skip solution treatment also? So that is our data at the moment. If you eliminate solution treatment, so we don't really know whether this is acceptable to the users or not. But this is for a specific material system, but I would like you to kind of think along those lines, right? If you're looking at a new material, but done by AM, maybe all the post treatments that you would otherwise do would be completely different, right? I don't want to show more data, it can get boring, but we've done all sorts of testing on it, and then in each case we show that the existing standards are not relevant, right? So, for this module, I hope I've been able to show you that post processing is crucial in case of AM, whether it is surface post treatment or thermal post treatment to get the mechanical properties that you desire. These post processing steps are material specific in case of thermal treatment. They could also be process specific in case of the surface post treatments that you do, right? But this for me is the most important, that the existing standards don't necessarily apply. Existing standards for traditionally produced materials don't necessarily apply to AM. Yeah. So, I am happy to stop here, but I can take whatever questions you have. Yeah. And I was happy to meet me, send me an email, and it will be nice if I am staying on campus anyway. Right? Thanks for your patience. Putting up with me for 3 hours or 4 is not easy. Yeah, but any questions now or later? Tired, hungry. Yeah.
Definitely, post-heat treatment will provide refinement of grain structure.
Oh, please be careful.
In aspect of textile material.
But ask your question.
Yeah.
Let me answer. Yeah.
Suppose if I go for heat treatment of a temperature below the solidus temperature, can I get refined structure? For additive manufacturing.
First of all, do you need heat treatment?
Yes, sir.
Yeah.
To refine structure. I mean, I would like to go for heat treatment so that I will get refined grain.
But you rarely do heat treatment to refine a structure, right? If you're doing heat treatment for accomplishing other things, let's say you want stress relief, yeah, or you want solution, I think, or stuff like that, then you want to ensure that you use a protocol that is appropriate for that, but ensure that there is no grain coarsening. Yeah, as we saw from some data at 1120 and 1185. Everything stays the same at 1120. 1185 suddenly you begin to see coarsening. So that's the operating window that you want to avoid. But I don't think you would do treatment to refine a material, especially in AM. I have not seen many users even wanting to do that. We could talk more. I think you are unhappy with my answer and I am unclear about your question. So, but we could take it further.
Yeah, one more question related. SIP we explained. I had a method called ECAP.
Yeah.
What is, can you comment in additive manufacturing case regarding ECAP? Advisable, not advisable?
As I said before, I would always avoid any post treatment if I had the luxury to avoid it. Yeah, if I can avoid not doing any surface post treatment, thermal post treatment, that's great, that's perfect, right? But depending on the application, I may not be able to avoid, right? So we spoke about different forms of surface post treatment. Yeah. For thermal post treatment, I would do a stress relief, or I would do heating. Yeah. To the extent that I know, the only guys who demand heating are the gas turbine guys at the moment. Nobody else requires it. Yeah. And we should keep it simple, as long as the end user doesn't demand these kind of post treatments, you must not get it. So for example, AM plus ECAP, I don't even know what is the merit of it. Yeah. Yeah, correct. I don't know. Yeah. Correct.
Severe process.
Disintegration.
Yeah. So why would you want to do that? I didn't. That's why I said I didn't understand your question, but you could talk more. I also, although I have worked so many years in coatings, I always say that if you can avoid coatings, avoid coatings. I mean, only if you have no choice, then you should look at all these things. Anyone? Yeah?
Sir, as the PLA material is very cheaper, so to do additive manufacturing. PL as a feedstock is very cheaper to do
PL.
polymer.
Yeah, okay.
But sir, metal, since it is very costly from commercial application and research application, so which kind of metal powder we should use so that research is cheaper?
Oh my God. Which kind of powder you should use so that the research is cheaper? That's a tough one. No, that's not how you should ask the question. But let's talk separately about it. Yeah. Research always happens once you have a problem identified that you want to solve. So what's the problem? Yeah. Well, I think once you're clear about the problem you're trying to solve, all these questions get answered. Yeah. What material? What process? Now all this will depend upon what problem are you talking about. Yeah. So at no time should you begin by asking what is the cheapest way to start research. No, it's not the right beginning. Yeah.
Sir, in electrochemical etching,
Yeah.
how you remove the support material without affecting the base matter?
That's challenging. Very challenging. So,
After support structure removal, we will go for that.
yeah, so
The sir mentioned that we can remove support sectors also using that.
they do
Structures
that.
are very thin,
Yeah.
simple.
But still, his question is very relevant because it's a dipping process. So I'm not sure if they do some sort of masking, if that is possible. But it's a good question. Let me check and see if I can get you an answer. It's still new. Hertization is extremely new and we can evolve it. So, and I think at every stage these kind of questions crop up. So I'm sure at the moment they think they can be done, but they have only been working on coupons, right, of the kind that I sent. So, but good question. Let me see if I can check and get you an answer.
Any other queries?
No?
we'll end the session here and we'll come back at 2:30.